Hi everybody, welcome to Lecture 38 of Thermodynamics. It's getting close to the end of the semester here. Hair is getting long. Stuck in the house for a very long time. And we're getting close to the end of the semester in teaching. So I'm hoping everybody's doing okay there, wherever you are. I'm going to talk today about the Brayton cycle, which is a special kind of gas standard cycle or air standard cycle that's used to model gas turbine engines and gas turbine power plants. So last time we talked about the Otto cycle. In the Otto cycle, we did an example of the Otto cycle, which is, as I said, was my favorite cycle. It's models internal combustion engines, specifically spark ignition engines. And if we look at the survey, we can see that about half of you got that right. So not that great. I look at the stats of how many people have watched the lecture, and it looks like maybe not everybody even watched my lecture. So I can see the motivation is dropping off. I want to let you know that we only have a few more left. There's only 3 more. There's this one, and then 2 more lectures. I may give an extra review video lecture, which I probably will do to run through some example problems set up before the exam, the final exam. So in a previous lecture, I might have said something about the final exam being something different than what we had for the midterm. But in talking to the TAs and in talking to colleagues, I think that probably it's best to just stick with what we've been doing and do a final exam the way that I did the midterm. Except this time, I'd like to make it a little less intense, maybe make it a little bit more such that if you do know some of the basic material, you can get the answers. As you notice that I put a pretty heavy curve on the grades of midterm 2, where I put everybody essentially the mean score at essentially about a 77.5, something like that, which is about an upper C. Some people didn't make the passing mark, but then one person got 100% in under the curved scenario. So the high raw score of the exam was about an 87%. Not great. I mean, especially compared to the first exam, albeit the second exam was much harder. So I guess maybe we'll find the happy medium for the final. So the final exam at this moment, I'm planning to be an exam during the scheduled exam time of when we're supposed to have this, and it's going to be a 2-hour long exam. So you'll have a couple hours to finish the thing and then turn it in just like the way we did the last one, like the way you do in the homeworks. I think that's the fairest and easiest way to get this done. And I didn't detect any foul play or anything in the first exam. I think that people were pretty stressed to get it done. I mean the second exam rather. So I really think that the exam, the format is probably okay. Maybe the way how difficult the exam was and how many problems there wasn't all that great for you guys. But I also think that maybe the learning experience is not quite as good as in person, which is affecting your learning. One thing that I have to just point out, and since I graded all the exams and all the problems myself, people are using the ideal gas law to model vapor systems that are like in two-phase systems, like steam. I know the ideal gas law is really easy to use, but it's wrong to use it for a two-phase system. If I say the word steam or water or R22 or ammonia or something like that in the problem, do not use the ideal gas law. It just makes me upset, and I just give you a 0. Okay, so that's not cool. You don't want that, and I really don't like that because I've said it so many times that I just feel like I'm repeating myself. So just to kind of reinforce that. So the Rankine cycle work that we did with the steam power plant, use the tables for that. Do not use the ideal gas law. For the stuff we're doing here, for the last lecture in the Otto cycle and for the Brayton cycle, use the ideal gas law. It's your friend when you're dealing with gases like air or nitrogen or oxygen. Those kinds of things are gases, right? They exist in the way superheated part. And as I said, very beginning of class, those things can be approximated like an ideal gas where PV equals MRT and everything is good. Okay? But if you're in a two-phase system like water or ammonia or R22 or some kind of refrigerant, you have to use the tables. Do not give me ideal gas law. You will not get credit for that because that is not the right assumption. Okay? Just another point of advice there. All right, don't make me upset. I don't like getting upset when I grade exams. Okay, let's talk today about gas turbine power plants and the Brayton cycle. Now, Brayton cycle, I could probably do an entire class in Brayton cycle. I could probably do an entire class. In fact, there is an entire class in internal combustion engines. But we're doing these each in 50-minute blocks. Okay? So you're not going to get everything. But I have a feeling that if you get some of it and you practice it, you'll get a lot of it. And you'll get most of what we need to know about these gas power cycles. Okay? So today I'm going to blow through quite a few slides here. You can see we're on 32 of 58. So I'm going to go through 32 to 58 and do an example at the end of the lecture. Okay, so that's my goal within this 50-minute block. Okay, so here we go. So gas turbine power plants are more quickly constructed, less costly, and more compact than vapor power plants that we discussed, the Rankine cycle plants. Gas turbines are suited for stationary power generation as well as for powering vehicles, including aircraft and marine power plants. And there even has been some turbine cars back in the 70s, but those didn't go very far. Gas turbines are increasingly used for large-scale power generation and applications fueled by natural gas, which is today pretty abundant and cheap. Okay, gas turbines may be operating in an open or closed configuration. The open gas turbine is more commonly used and is the focus of our study of gas turbines. Okay, the open one is sort of in the left figure here. The closed one is on the right. Now, the one that is called an open Brayton cycle essentially operates as a series, or both Brayton cycles operate as a series of control volumes. Okay, steady state control volume devices, like we did for the Brayton cycle, the Rankine cycle, except the Brayton cycle has gases, and we of course assume an air standard cycle like we have with the with the Otto cycle. Okay, so the study of individual components of these configurations require the control volume forms of mass, energy, and entropy balances. Okay. So you can see that essentially a gas turbine engine, if you just consider the open cycle, consists of a compressor. So we take air in, compress it, combust some fuel and exchange heat, and then use that hot gas to expand in the turbine, and then we exhaust the turbine products out the back of the turbine and make net work. Okay, the closed cycle essentially uses the same working fluid but uses a heat exchanger inside. And the heat exchanger reclaims that heat and sends it in the compressor. Sometimes this is called a regenerator or recuperative system. Excuse me. Okay, so considering the gas turbine power plants. The open mode of the gas turbine is an internal combustion power plant, or internal combustion power plant. So air is continuously drawn into the compressor where it's compressed to a high pressure. And then air enters the combustion chamber where you mix with fuel and then combustion occurs. And then you have the turbine combustion products, or you have the air and fuel, they burn inside there. You have combustion products go into the turbine, they're hot, and they expand through the turbine and it comes out colder. Okay, so this is typically how a gas turbine works. Oh boy, keep on moving myself around. Okay, let's see. The closed gas turbine operates in the following way. So the closed gas turbine assumes there's a heat exchanger, and there's just the one working fluid that goes around, right? And a heat exchanger that drags the heat out of the gas, and then the air goes into the compressor. Okay? And this Q-in isn't necessarily mixing air in. Okay? Essentially, it's just a heat exchanger that some combustion gases go through a heat exchanger, kind of like the boiler. And they heat up the gases, and then goes to the turbine. So as the gas passes through the higher temperature heat exchanger, it receives energy by heat from an external source, just like this one, and then a heat exchanger on the bottom side. So most of the Brayton cycle that we analyze is sort of like this, except that we just assume that it's an air standard cycle. But the heat transfer associated with the high temperature heat exchanger of a closed gas turbine originates from an external source, which could include like external combustion, or solar heat, or gas, or a nuclear reactor. Okay, the efficiency of the system is not as high, but the ideal efficiency, as we're going to find out, is not as high as the Rankine cycle. But it is a pretty useful thing to do, especially as I said, because it's cheaper and the equipment is smaller and easier to install. So what we're going to do is we're going to conduct an elementary analysis of open gas turbine plants, the air standard analysis, so that we can provide insights about what happens in real Brayton cycles or real gas turbine power plants. In an air standard analysis, the following elements. So we have air. So we assume it's all air. There's no combustion, just like we assumed with the Otto cycle. We don't assume combustion. We assume everything is air. The temperature rise brought about by combustion is accomplished by heat transfer from an external source. With an air standard analysis, we avoid complexities of the combustion process and change composition during combustion, so we don't worry about that. We just assume it's all air. So the whole cycle is air. In a cold air analysis, we can even further assume that the specific heats are constant, like I did with analysis of the efficiency of the Otto cycle. So we could do that too. But I'll tell you whether you can use the cold air assumption or whether you can use constant specific heats. Okay, the air standard Brayton cycle looks like the following then. The schematic of a simple air standard cycle is shown in the figure. The air circulates through the following components. So 1 to 2, you have air compression through the compressor. 2 to 3, you have a heat exchanger. And 3 to 4, 3 to 4, you have high pressure, high temperature air expands to the turbine. And then air returns to the surroundings at state 4 with a temperature at a temperature greater than state 1. Because you can't have the same temperature run by like the second law, because then you wouldn't reject any heat from the cycle. You wouldn't have a Q out. So then what we assume then, and this is kind of an important factor about the Brayton cycle, open Brayton cycle, is that we assume we have some sort of fictitious heat exchanger, okay? So the exhaust empties into the air, and the air is a huge volume. It reduces the heat somehow, right, by cooling with the environment, and then new air comes into the compressor that's cooled, right? So essentially there's some heat rejection just because you've dumped hot stuff in the environment and the environment cools it, okay? So in this case, we assume that the environment is this heat exchanger, the dotted line here. But really, it's kind of a closed system, but we're just assuming that this heat is just dumped, right? By rejecting air into the environment and then bringing new air in. So it's still an air standard cycle. It's just that there's not a specific heat exchanger. We just assume it's sort of like a fictitious heat exchanger. And then 3 to 4, the high pressure through turbine, the 3 to 4, and then air returns to the surroundings at state 4 with a temperature typically much greater than state 1. After interacting with the surroundings, each mass of air returns to the same condition entering state 1, thereby completing a thermodynamic cycle. So we can imagine process 4 to 1 being achieved by some magical heat exchanger, as I said, that exchanges heat and reduces the temperature back down to state 1, so you can complete a cycle. So cycle 1, 2, 3, 4, 1 is called the Brayton cycle, and the compression pressure ratio P2 over P1 is a key parameter of the Brayton cycle, which we will discuss. So the two things I'm going to talk about are three things. The first is I'm going to develop the basic Brayton cycle analysis, which are all analyses that you've already done. So we don't need to belabor compressors and turbines and heat exchangers because we already did those. However, putting it together as a cycle we haven't done yet, so we'll do that. The other thing we're going to do is we talk about the pressure ratio and how that affects the efficiency of the turbine. And then the third thing is we're going to talk about is irreversibilities, just like we did with the Otto cycle and with the Rankine cycle. Just talk about what irreversibilities there are, common irreversibilities, and how we model those. Okay, so the air standard Brayton cycle it has these 4 processes. I guess they're starting with turbine. Starting with the compressor, going through heat exchanger, turbine, and heat exchanger, and they look like the following in terms of the first law. So we write the first law for each thing, each individual control volume, and we get the following. So compressor down here in the bottom left is the work, little w equals H2 minus H1. And then you have from 2 to 3, you have a heat addition, which is Q in, which is H3 minus H2. And then you have heat rejection. So you notice it's the same kind of thing as that we had for the other cycles. It's just that we've got H's here because remember we have flow going through these things. So it's flow work, we have to use H. Okay, remember that. Okay. All right, so then we typically assume that the compressor and the turbine are adiabatic so that their heat is 0. And we typically assume that there's no work going on in heat exchangers, which we already know. We always assume there's no work going on in heat exchanger. There's no shaft work and the volume's not changing. So essentially, we've got the following really simplified first law equations, okay? The parameters, of course, that we have to consider are the thermal efficiency, which is given here, which is the net work, which is turbine minus compressor work, over the heat in. So it's what you want over what you get out over what you put in, which is the first law efficiency. The back work ratio is something we calculated in the Rankine cycle example, and that is equal to the work of the compressor over the work of the turbine. You're going to find here that the back work ratio for gas turbines is ranging about 20 to 80%. So it's a lot compared to the 1 to 2% for vapor power cycles. And the reason is because it costs a lot of work to compress a gas versus pumping a liquid, just because the incompressible nature of it. Okay, so it's just going to cost a lot more to do that, and the back work ratio is going to be higher. That doesn't mean that the cycle is less efficient. That just means you have to take more of the work that you make from the turbine and put it into the compressor as part of the cycle. Okay, so since these equations have been developed from mass and energy balances, they apply equally when irreversibilities are present in them presence. So these are just based on, you know, the standard standard thing here. So of course this only applies when you have an adiabatic system, right? Because you can't just assume that the turbines are adiabatic if this work does not necessarily equal to H3 minus H4 because there could be a Q term in here and whatever. But in the case of an adiabatic system, it's fine. And if it's irreversible, you still have the same. You just have to know what the actual H's are to calculate it. Okay? So the ideal air Brayton cycle provides a especially simple setting for gas turbine power plant performance. The ideal cycle assumes that there's no friction, there's adiabatic and reversible, and they're called isentropic, as we know, processes. The ideal Brayton cycle consists of two isentropic processes alternating with two isobaric processes. So it's not like Carnot because they're not isothermal, they're isobaric. The ideal Brayton cycle is in harmony with the ideal Rankine cycle, which consists of two isentropic processes with two isobaric processes. Okay. Okay. Yeah. All right. So they're isobaric in the Rankine cycle too. They're mostly isothermal, but because they go across the vapor dome, they're isobaric and isothermal for proportion except for the boiler, which we've discussed. Okay. So air standard Brayton cycle. Number 2. We have the following PV and TS diagrams. Now, these have little things on them because I'm sure there's an animation in here, and I'm going to get rid of these because they're annoying. Let's just get rid of these because I'm not showing any animations, and animations are annoying anyhow. Okay, so here we go. So the air standard Brayton cycle consists of the following internal reversible processes. 1 to 2, isentropic compression. You see, we're compressing. This is an isentropic curve. You can see 1 to 2 is straight up and down vertical in the TS diagram. 2 to 3, isobaric. So PV on the PV diagram, 2 to 3 is horizontal. And then you have, so in this case, you have a slope, right? Because you have temperature increasing even though the pressure is staying the same. And then you have 3 to 4, which is a drop in pressure, but reversible in adiabatic, so isentropic. So it means that the line is totally vertical going down. And then likewise, you have another isobaric heat rejection process, which is given by 4 to 1. And so you can see that typically the PV and the TS diagrams are useful for the Brayton cycle. You can, I don't know, TS is probably all you need, but the PV diagram is also good to use, and I would suggest being able to make both diagrams for both cycles, even the Otto cycle, if you can make a TS diagram, which I don't think I drew, but are in the notes. So I would recommend being able to make a PV and TS diagram for both air standard cycles that we're going to cover, we have covered in this class. Okay. So since the ideal Brayton cycle involves irreversible processes, results from chapter 6 apply on the PV diagram, unit of mass. So we can obviously look and see that the area under the curve, oops, this is really kind of weird. I don't know what this is all. So the area under the curve is the heat, and then the network is this area here, and then this area here gets subtracted out. So they made a little drawing here, so that's better. So essentially the area that we have, the PV diagram, on the VDP, so to the left, and because it's an isentropic process, is the work that you have, the work that you have done, and so that the work within the diagram is the network. So the area 1, 2, 3, 4, 1 is the work in the network. The area from A, 3, 4, B, A, essentially in this case, is the overall work, or the work out, the turbine work. I hope that makes sense. That's the area under that curve to the left, because VDP. Okay, on the TS diagram, the heat transfer per unit mass is TDS, so therefore the heat transfer is this thing right here, which is a little funky. But you get the idea. It's the area under the curve. So the overall Q in is the area given by AB23A, and the overall, if I just take this out, I don't know where this is, but oh yeah, there it is right there. So I get rid of this. So this area right here. So that's the net heat, and then the overall is that one right there, right? The overall is the entire area, the overall is the area inside the curve, whereas the heat in is the heat in is the area, the big area, and then the heat out is this smaller area in the bottom. Okay, and then the subtraction between those things is the net heat. Okay, we've done these kinds of things before. Okay, so the thing that we want to talk a little bit about is the effect of compressor ratio, pressure ratio, P2 over P1 on gas turbine performance. So this is analogous to the discussion about compression ratio, the V2 over V1 for Otto cycle, right? So the pressure ratio is something we can control by changing the pressure of the turbine. So you can just crank down the turbine, you can make it, the compressor, you can make more pressure, which then gets higher pressure in the combustor, which then you get more pressure in the turbine, and you can change the pressure ratio. On the bottom, you can't change the pressure so much because the bottom is governed because that's the atmospheric pressure usually, because it's drawing, you have a compressor that's drawing air from the environment. So that pressure is kind of atmospheric. So this pressure here, 1 to 4, is the atmospheric pressure. So there's not much you can do to reduce it. Like in the Rankine cycle, we could reduce the condenser pressure. We can't do that in the Brayton cycle. We kind of have to leave 401 as the same, but you can always crank the pressure on the high pressure side. So what happens when you do that? So when you do that, increasing the compressor pressure, so if you go to 1, 2 prime, 3 prime, 4, you have more heat, right? And you have greater average heat of the cycle. So therefore, you have the same heat rejection, but you have a greater thermal efficiency because you have a greater area inside the curve. So actually, changing the pressure ratio is an advantage because you have more heat available. So changing is a good thing. And you can see here, you can make a plot of what that looks like. So you can plot thermal efficiency as a function of compressor pressure ratio, and see that it increases as you vary that. So the Brayton cycle thermal efficiency increases as the compressor pressure ratio increases because of that. So you can make sort of first law arguments as to why that is. Okay. So increasing the pressure ratio changes the pressure. So since the average temperature of the heat addition is greater, does this say anything what we've already said? No, not really. So this pretty much says that we increase the pressure as we increase the pressure ratio. However, there's a limit on the maximum temperature of the turbine imposed with metallurgical considerations. So you would always want, so for instance, go back here, you always want to increase the pressure ratio. And you say, well, just crank it as high up as you can go. However, there's a problem in that 3 prime is typically a limiting factor. So when you add that heat to get to this other to get through the heat addition of the Q in process, you can't put too much heat in, because what happens is you end up getting a problem with melting turbine blades. You don't want to be on an airplane when your turbine blades are melting. That's bad, right? So 3 prime, or that 3 point, is really the maximum. It sets the maximum that you can be. So there's a couple things you can do. Okay, so if you say, well, I can absolutely not tolerate anything more than 2,000 K on my turbine blades, or else they're going to melt, and we're all gonna, whatever. So it's not good. So what you want to do is make sure you maximize, you get that T3 as a limit, but then change the pressure ratio accordingly. So you can do a couple different things. So you could do this. You could have a really high compression ratio, but then not add very much heat. So, and then you can say really high pressure ratio, and then you just add a little bit of heat. So cycle A has greater thermal efficiency than the baseline cycle. Cycle B has a larger enclosed area, so has the greater net work developed per unit flow. So essentially, the area B here, 1, 2, 3, 4, is a cycle that has more area, so there's definitely a lot more workflow, even though it may not be as efficient because the pressure ratio is lower. So you have to decide, for cycle A to develop the same net power as cycle B, a larger mass flow rate would be required and indicate a larger system. So essentially, since cycle A has a larger efficiency but doesn't make very much power, you need to have a really big system, like more flow rate, and the system would need to be bigger, which would cost more. So usually what happens is there's a cost trade-off. You say, well, there's pressure ratio, which we want to be high to have high efficiency, but we don't want it to be too high so that we can't put very much power in or much thermal input into this thing. The Q in has to be small, because you can't exceed the T max, which is this turbine inlet temperature maximum. So what that means essentially is that you're limited within this bound to develop a system that has a good trade-off between cost and efficiency. Okay, size of the unit, versus the efficiency of the system, and that tends to be an economic thing less than a thermodynamic thing. But you can see how that plays out in terms of efficiencies. It's very similar to the compression ratio argument we were making before for Otto cycle. So, accordingly, for turbine-powered vehicles where size and weight are constrained, it may be desired to operate near the compressor pressure ratio for the greater net work per unit of mass flow, and then not the pressure ratio for greatest thermal efficiency. Right. So, like if you have a jet engine for a fighter jet, which is a gas turbine, you'd want to operate like 1, 2, 3, 4 here. We want the maximum amount for the smallest package. So you may not have a very efficient engine, but you've got one that has a lot of power for the given size. Whereas if you are talking about a gas turbine power plant, maybe you want to increase the pressure ratio, but make it smaller and make the thermal input smaller per unit mass, but then you build a bigger system because you've got a big building to put it in. So you might as well make it bigger to the point at which you can't afford it anymore, and the metal becomes too expensive. Okay, so that's an interesting constraint. Okay, we're almost done with the slides here. So the other thing we want to talk about, so that's pressure ratio. The other thing we want to consider is irreversibilities. And for a gas turbine, the irreversibilities by far, of course, is combustion, which we said was the same thing for the Otto cycle. But we're not analyzing combustion. We're just assuming heat comes in. So really what we're going to do is we're just going to assume that the only two irreversibilities that are really relevant to us are the irreversibilities through the turbine and the compressor. So they're each going to have an efficiency. And so that's what we're going to do. Right? And so the diagram becomes like this. So the TS diagram kind of looks like this. So we assume that you could also have pressure drop in the heat exchangers, but we don't assume that. That's not typically something we get that worried about. Typically, what we're worried more about is the efficiency of the compressor and the turbine. So here in this case, you have a 1 and 2s, which is the isentropic portion, and then you have 1 to 2, which is the non-isentropic, the actual cycle. And what you need to do is use the isentropic efficiencies, like this one here in turbine equals H3 minus H4 over H3 minus H4s, to determine what the actual enthalpies are at the end of those things. And I believe, are we doing this? We're looking at our example problem. It doesn't look like we actually do. It looks like we're just using doing a nice ideal cycle analysis. But you can use the same methods that we were using in Rankine cycle to do this analysis. And then likewise, the isentropic compressor efficiency is the same thing, which you should review and make sure you understand how to do this. Okay, so those are the main irreversibilities, and you can go through and calculate those just like you could for the pump in the turbine for the Rankine cycle, and do the same type of analysis to get the actual states 2 and 4. The important thing to note is that for this case, we assume that 1 is the same, because that atmospheric pressure at some temperature, at some state, we don't assume that it changes. In point 3, we don't assume changes either, because point 3 is the peak temperature from the combustor. So we don't actually change that very much either. So essentially, the pressure ratio is fixed. So really the only 2 points we're changing with the irreversibilities are 2 and 4, right? And so that's why those two are the ones that have a little bit of a slant to them, right? They're less efficient. They make entropy generation goes up, which affects the overall cycle efficiency. Okay. Now here it is time that we do our example problem. And I'm going to try to go take this example problem through and solve it. Let's see if I can get it on my iPad here. So let's go to the iPad here. Here it is. Okay. Oh, Braxton cycle. That must be a spell check error here. I don't know what Braxton is, but it's certainly not what we're dealing with. A-ton cycle. Brayton cycle. Okay, here we go. Good. So Brayton cycle, yeah, see that has that doesn't go with the spell check. So Brayton cycle is actually something real. Okay, so the air enters the compressor of an air standard Brayton cycle with a volumetric efficiency of 60 meters cube per second at 8 bar and 280 K. That's about atmospheric. The compressor pressure ratio is 20, and the maximum cycle temperature is 2100 K. For the compressor, the isentropic efficiency is 92. Oh, yeah, we do have efficiencies. And for the turbine, the isentropic efficiency is 95%. Determine the net power developed in megawatts, the rate of heat addition to the combustor in megawatts, and the thermal efficiency of the cycle. Okay, so we can do this, no problem. So let's go here. What we have here is that we have a air standard Brayton cycle, and with non-ideal turbine and compressor. Okay, what we have to find is the power. So this is W dot. And we'll just call that net. We need to find the rate of heat addition to the combustion, so we need to find Q in. Uh-oh, it's Lola. She's ready to do thermodynamics again. And she's kind of grumpy. She wants attention. And the last thing is we need to know is the thermal efficiency. Okay, so the thermal efficiency is the last item that we need, right? Part C. Okay. So what are we going to do? We're going to make some assumptions here. Okay, so the assumptions are A, it's air, standard, not constant specific heats, because we didn't say cold air cycle, unfortunately. So B, let's see, anything else we need to do? Air standard cycle, we'll just say, because that takes care of all that stuff. We have non-ideal turbine and compressor. C, we assume it's all at steady state. All right, so steady state meaning that we can just analyze it the way we typically analyze these things. Okay. Okay, now let's see. We are going to now go through here and make our diagrams. So diagrams, we have a couple diagrams. First, let's make our system diagram. All right, so we're gonna have a turbine and compressor system. I guess we'll call this the turbine, and then these things are generally connected together. So that's the network. Okay, and then we have, so the compressor kind of goes in like this. This is compressor, like this, and then we go into a kind of a heat exchanger. Do we have a regenerative cycle here? I don't think so. Compressor and turbine. No, I think we're good. I think we've got. No. I think we're good here. I think we're good. I think what we need to know is the we have a pretty much an open cycle. Oops. So the compressor comes out and yeah, I think we're good. Okay, so then essentially we have a we have some heat addition process here. So we have Q in, and then at the bottom we've got some Q out. Going in here with our heat exchanger here, we have Q out here, and then we have some work into the compressor here. Okay, so that's essentially what we've got, and this is our system diagram. Now we also have a TS diagram to make. We got to make our TS diagram because that's a real kind of essential thing. So now we have TS. So we have pressures. You know, we have 0.1 here, so T equals, what did I say, 280? Oh yeah, we have to label our states here too, so let's do that. So we're gonna go inlet of the compressor, so 1, 2, 3, 4. And then, of course, we've got isentropic, the ideal Brayton cycle with isentropic processes goes like this. and then 1, 2, 3, and then 4. So it looks kind of like this. And then this is for S and 2S, because actually what your processes are doing is this. So we have 2 and 4 look like this, because they're on the same, these are constant pressure lines. P equals constant, right? So this one is at, what did I say? It's over a pressure ratio of 0.8 bar down here. And then it's also, and it's a maximum pressure of 20. So it's 20 times that. What did I say? Oops, stop that. Stop that. Okay. Okay. And then here we have a pressure of, what did I say, 20 times that. So that's it's 16 bar. Right? So it's 1.6 times 10. So it's, yeah, 16 bar. Okay, good. So then we've got that. We don't know much else. I guess we know the peak temperature. We know 2100 is our peak temperature. That's T3, right? Okay. So that's about all we need to do. So let's go example 1 continued. Now we have the example with the analysis of our problem. Okay, so now we have the analysis of our problem. So first let's get the states. Let's see. So T1 is equal to 280K, right? So then we can look at the table for air. And we know H1 equals, so look, we're getting H's now, not U's. U's were when we had a fixed volume or a closed system like the Otto cycle, right? But for this system, we don't. We have to consider the H. So 280.13 kilojoules per kilogram. And then I think we need PR, right? It's PR1 equals 1.089. Because we have an isentropic compression, well, at least part of it is isentropic compression. So state 2, so this is state 1. State 2, we know that PR2 is equal to P2 over P1 times PR1 for an isentropic process only. Right, because we can get the real pressure here. So PR2 is equal to 20. The pressure is 20 times, because the pressure ratio is 20, right? 20 is the pressure ratio times PR1, which we say is 1.089, which is equal to 21.778. And then so from the table we can get T2S, which is the isentropic temperature, which is equal to 649.3 K, and H2S is equal to, what is it, 59.13 kilojoules per kilogram, right? So then, but that's S, right? So we need to use the efficiency. So we know that the efficiency is equal to H2 is equal to H2, it's H1, because H2 minus H21 plus H2S minus H1 divided by the efficiency of the turbine, which we know, which we're given as, what is it? The compressor, is 92%. So, all right. So if we just put it in our numbers for this, H1 is 280. That was supposed to be a 280.13 plus H2S, which we found is 659.13 minus, where am I at? 659 minus 280.13 divided by 0.92. And this ends up giving us 692.09 kilojoules per kilogram. Okay, so then we got that one, and we got, so really what we're looking for are the H's, right, to do this analysis. So H1 is here, H2 is there. State 3, we go to the next one. So state 3 is constant pressure, right? So we know that the pressure is the same, but we know the temperature. Kitty, you got lots of hair. Okay. T3 is equal to 2100 K. T3 is equal to 2100 K. And then we can look that up because we know 3, remember, only a function of temperature for ideal gas. This is an ideal gas. You can use ideal gas law. I don't want you to scare you away from that, but you can. 2377.4 kilojoules per kilogram. And then PR3, which you'll need to do the isentropic analysis, is equal to PR3 equals 2559. Okay, so that's not unit, it's unitless, so we don't have units on PR because PR is just a ratio. So if you want to find the actual temperature, we know PR4 is equal to P4 over, P4 over P3 times PR3, which equals 1 over 20, because we assume no pressure drop, so the PR3 over PR4 is 20, times 2559 is equal to, the P4 then is equal to, 127.95. So that's this PR. So then we can look up in the tables by interpolation. So we can find out by interpolation that T4S is equal to, so this is the isentropic, remember, because this is for when you use PR, you're finding the isentropic process. 1029.2 K, and H4S is equal to, we're almost there for this analysis. Once you've got all the states, these things are pretty easy to do, is equal to 1079.4 kilojoules per kilogram. Now, if we actually want to find the isentropic turbine efficiency, so we know H4 is equal to H3 minus isentropic turbine efficiency H3 minus H4S. Because it's the opposite, the ratio for the compressor and turbine are inverse, right? As we remember from doing those. So H3, hopefully you practiced those a little bit. 2377 minus 0.95, which I believe is what it is, right? Yeah. Times 2377 minus, what do we have? H4S is 1029, right? 1029, or is it 1079? My handwriting is not so good. Where is it here? 1079. So that's 1079. Okay, and so this gives us H4 is equal to 1144.3 kilojoules per kilogram. Okay, so now we have all those things. Now the only other thing we need is, since they're actually asking for power, we need to know what m dot is. So m dot is equal to, let's see, we want the velocity, so we need, we'll call this v dot, which is the meter squared per second that we were given, times p over rt, and this is was 60 meters cubed per second times p, which is 0.8 bar. We're gonna have to get in the kPa, so we're gonna have to have a factor of 100 here somewhere. 8.314 divided by 29 approximately for air, times 280 times, 100 kPa per bar, right? So then we get an m dot, which is really what we want, 50 9.73 kilograms per second in SI units. So now we really have everything. Now we can actually solve the problem. We can solve the problem. Okay, so work of the compressor is equal to m dot h2 minus h1. So that's how much work the compressor is doing. 59.73692 minus 280. And this ends up giving us in kilowatts 2.461 times 10 to the fourth. Woo, that's a pretty powerful turbine. Kilowatts. Really powerful, right? Yeah, that's a mega turbine. So that's 24 megawatts. Okay, so B, 24 megawatt turbine. That's a big turbine. Okay, well, no, we're not B because we need to find the network. So let's find work of the turbine then is m dot h3 minus h4, which equals 59.73 times the same mass flow, because the mass flow is the same, right? It goes all the way around. It's in a cycle, so we can just use one mass flow. 2377 minus 1144, and this is equal to 7.365 times 10 to the fourth kilowatts. So almost 74 megawatts. So 74 minus 24 net is equal to, well, we'll just say 7.635 times 10 to the fourth minus 2.461 times 10 to the fourth, and that is equal to 4.904 times 10 to the fourth kilowatts, which equals to 49 megawatts. Okay, so part B is to find Q in. So Q dot in is equal to m dot h3 minus h4, which is equal to, as we know, 59.73 times, what are we doing time? Oh, perfect. 59.73, 2377 minus 1144, which is the h3 minus h4. So once you get to this point and you have the h's, this is really not that difficult, right? You're just kind of plugging them into the formula. And this is equal to 1.0066 times 10 to the fifth kilowatts, which is about 101 megawatts of power. 101 megawatts, okay? Now, C then is the efficiency is equal to the work over the Q cycle. So we'll call this work net over Q in. And this is equal to work net, as I said, 49 over 101, which is equal to 48.7% is the thermal efficiency. Okay? So that's your thermal efficiency of the cycle. Now, the last thing we could do in our last remaining minute here is to calculate the backwork ratio. Just to see what the backwork ratio is. Why not, right? Because we have it. So it's the work of the turbine over the work of the compressor over the work of the turbine. So it's about 24.6 megawatts over 73.7 megawatts, and this is equal to, we get out my calculator here. Why it's not looking at my face for some reason. Okay, so here we go. So we just do this final thing. We go 24.6 divided by 73.7, and that is equal to 33.3%. So that's the backwork ratio. It's a lot higher than the Rankine cycle example we did a long time ago, where we had 1% backwork ratio. So definitely a lot higher, and but it still has a pretty high thermal efficiency, 48%. Okay, so that gives you an idea of how to do the Brayton cycle. Please practice it. You'll have an opportunity to practice a cycle or two for your homework, and hopefully you'll be able to follow this example in order to do those. Okay, so great. Look forward to talking to you again on Friday.